Okay, so we're still on Unit 1, but Unit 1 consists of Chapter 1 from the textbook and Chapter 2. So both are considered functions. So the first part of this unit was characteristics and properties. This part is all about rates of change. Okay. Before we get into the nitty-gritty of what that means, we're first going to do this bonus topic called radical expressions, rationalizing denominators. Because what's going to happen is there's going to be something coming up within this chapter, specifically when we deal with the second bonus topic, where it'll be important that you understand this strategy. So we're going to do the strategy, and you're going to we're going to do some examples. If you look at the back of this sheet in your notes, you'll notice that's where the homework is. It's from another textbook that has the sample questions. Okay? So let's go over what this means. So in radical expressions, we never like to leave a radical in the denominator. The process of changing the denominator so that it becomes a rational number is called rationalizing the denominators. Remember, a rational number is a number that can be written as a fraction, so meaning basically not a square root number. Okay? And so if the denominator is a single radical, multiply the numerator and denominator by the exact same radical. So you might be familiar with this from trigonometry. Do you guys remember that sometimes this value showed up as an answer to one of the special angles? Sine of 45 degrees was 1 over root 2. If you went back, remember this is like flashback, remember this? Is ringing a bell? Or it might have been two, yeah, I think this was it, right? Or two, yeah, I think this. So basically, if you wanted, no, it was not this. See, this is what happens when you do things without thinking. Okay, so that's better. Okay, 1 root 2. So when you did like sine of 45, 1 over root 2. Okay, so basically, I don't know if Mr. Tranch said, well, a nicer way of doing this, or the textbook, is to rewrite it by multiplying by root 2 over root 2, because what are you really multiplying by? 1, right? Root 2 over root 2 is really just 1. And then you end up with root 2 over, what's root 2 times root 2? 2. That's rational. Okay? So that's rationalized. You just rationalized the denominator. You made the denominator rational. Okay? And so if the denominator contains the addition or subtraction of a radical number and an integer or 2 radical numbers, multiply the numerator and denominator by the conjugate of the denominator. Same values for the 2 numbers, but change the sign between them. So example of that would be something like this. Okay, so now, again, you don't have to write this down, we're going to do examples, but just to give you an idea. If I try to use the same strategy as I just did there, I'm going to have a bit of a problem, because if I multiply this by root 2 over root 2, you're like, whoo, okay, good thing that root 2's gone, but uh-oh, because what happens? Now you have to distribute the root 2 to both parts. You're now stuck with a 5 root 2. Oh, I'm going to get rid of this root 2. Times root 2 over root 2. Do you guys get where this like never-ending loop of root 2's over root 2's? Okay? So it's never going to end. So that's not the strategy to use. The strategy is you multiply by something called the conjugate. So the definition of a conjugate is same values, but change the sign between them. So the sign right here is plus, so I'm going to write root 2 minus 5. And you do the same thing with the numerator. And so what happens is, if I don't know, this, I don't know what I'm doing. Okay. So basically, what this means is you kind of created, I'm going to say, a difference of squares pattern. Are you buying into that? Because what do you notice about when you expand, if you multiply the denominator, you would go root 2 times root 2. What's that? 2. Minus 5 root 2 plus 5 root 2. Oh, look, the middle cancels. Positive 5 times negative 5. But when you simplify it, it's going to be rational. Okay, and then the numerator is just that times 1. So your numerator ends up being like still have a radical in it, but now you have root 2 minus 5 all over negative 23, something like that. And are you going to leave the negative 23 in the denominator? We don't like that as math people. I'm going to write this and you tell me, do you buy that this is good? Yeah. If I bring the negative to the numerator, something I could do then is distribute the negative, and so that would just flip the order. Okay? So I basically just did a random extra example just now, but just to give you the idea of how that works. Let's actually do some ourselves. So 3 over 4 root 5. So the key here is you don't have to multiply by the denominator, just the radical part of the denominator. So 3 over 4 root 5, I'm going to multiply by, is everyone happy? I'm going to use the dot for multiply. We're advanced enough, I think we can handle this, okay? So times by, what's the radical part of the denominator? Root 5. The root 5. So that's what I'm going to multiply by, and I'm going to do the same to the numerator. Because the goal is, the only thing you're allowed to multiply a number by so it doesn't change the number is 1. So it always have to be same over same. That's what you always have to multiply by. So root 5 over root 5. So now actually multiply the numerator. 3 times root 5. Think of it like there's like that root 5 where there's like a 1 in front of the root 5, so you're multiplying the numbers outside and the numbers under the root. So you just get 3 root 5. Okay, so 3 root 5. For the denominator, what are you going to get? 20. Is everyone good with why we get 20? Okay. And then in some random cases, what might end up happening is you might have to reduce, like if that had been 5, do you guys get what I mean? Like if the 3 had been a 5, you would have had 5 root 5 over 20, and then you could, 5 and 20, you could reduce 5, 20, 1/4. But in that case, you can't reduce. But just be prepared, you might have to reduce. And your denominator is a rational number, and we're happy campers. Good. Okay, example 2, 2 over root 6 plus root 3. So this time, 2 over root 6 plus root 3. Am I going to be able to use the single radical strategy for this one? I'm going to have to use that conjugate strategy. So what's going to be the conjugate? I'm going to multiply the numerator and the denominator by here. Root 6 minus root 3. Okay. Root 6 minus root 3. Okay. So for the denominator, remember, it ends up being a difference of squares pattern. So basically it means square the first radical minus the square of the second radical. So what's that end up being? It's going to be 6 minus 3. Is that good? Okay with what just happened there? Root 6 times root 6 is 6. The middle terms will cancel. Positive root 3 times negative root 3 will be negative 3. So there's your 6 minus 3. For the numerator, okay, what I would recommend you do is leave it like this, because maybe that reduces and you can cancel. Does that make sense? So you don't want to distribute it and then have to cancel it. So I will leave it for that for a second. I'm just going to press pause for a second, guys. So we have a visitor. Okay. Like an announcement or something. Okay. Okay, so then we're going to just I'm trying to just kind of give you some good strategies here. So once you have it like that, and you know that the 2 and the 3, there's no reducing there, if you left your answer like that, I'd be maybe kind of willing to say check mark and give you the mark. But if you wrote 2 root 6 minus 2 root 3 over 3, that's also fine. Does everyone see those are the same? They're equivalent expressions. Either one is correct. But if the 3 had been a 4, you guys get, I would have expected you to reduce it. Yeah. So that's why I said don't distribute it right away, because maybe you can reduce. Okay. So for the last one, 5 over 2 root 6 plus 3. So what am I going to be multiplying numerator and denominator by this time? 2 root 6 minus 3. Good. You need it to be same, opposite sign, same for it to work. Okay? Okay. So now, be careful with the denominator. because there's a couple things happening here. When you do 2 root 6 times 2 root 6, what's the result there? Careful, 4 times 6. So everyone see what just happened there? Because the 2 isn't under the root, so 2 times 2 is still 4. 2 times 2 did not suddenly become 2. Okay? So 2 times 2 is 4, root 6 times root 6 is 6. And then what's the middle, again, the middle terms cancel. What's the last number going to be? Minus 9. Now numerator-wise, again, I'm going to leave it like this because I don't know, maybe something kind of nice is going to happen here. Wink, wink, nudge, nudge. Okay? So I'm going to leave the 5, 2 root 6 minus 3 all over. You could do a step where you just multiply 4 times 6, but I think you can handle 4 times 6 minus 9. 15. Hey, do you see why we didn't distribute the 5? Sorry, I'm too excited about this. Okay, so we didn't distribute the 5 because, hey, look, 5 and 15 reduces to what over what? So 2 root 6 minus 3 all over 3. And I'm hoping we all realize this would be completely illegal. Illegal, against the law. Don't do that. Okay? Okay. So we're good? Do you guys want me to prove to you why that's illegal, or are you okay why it's illegal? Okay, I'll make it with simpler numbers. 5 plus 2 over 2. Does that equal 5 people? Does this make sense? 7 over 2, not 5. So it's same reasoning, okay? Order of operation. I'm making Amy laugh a lot. Okay, so guys, in some weird cases, it might make more sense to rationalize the numerator, meaning we want the numerator to just have rational numbers, and we actually want the denominator to have a radical. You'll know when it comes into play. It's not going to be, if you're asked to rationalize the denominator, obviously rationalize the denominator, but in some cases, rationalizing the numerator might be the strategy. So just do that here, rationalize the numerator. So it's the exact same procedure you just did. Instead of the denominator being a rational number, I want the numerator to be a rational number. So right now the numerator has radicals, I want the denominator to have radicals. So root 7 minus root 3 all over 2. To rationalize the numerator, I need to multiply the numerator and denominator by plus root 3 all over, same, root 7 plus root 3. Okay. So now my numerator becomes 7 minus 3. Denominator, again, avoid the distributive property right away. Can you tell that I like planning these out to a T? Okay, I'm like, because what's 7 minus 3 people? 4. That's neato because what can you do? Yeah, you're allowed to cancel there because the 2 is multiplied by this. That's the key. That's when you're allowed to cancel. When things are multiplied and it's multiplication, you're allowed to cancel. So 4 divided by 2, you're left with 2 over 1, if you will. Okay? So you have 2 over root 7 plus root 3. Okay? Any questions? So that would have been a really short lesson if I stopped. Okay, so that was literally going to be my lesson today, and then tomorrow I'm listening. But anyway, the vote was I do 2.1 as well. So here we go. Okay, So, rates of change. We've been studying rates of change since pretty much grade 9. Because a rate of change is just how fast a graph changes. Can you think of something that would, well, let's look at this definition. Determining average rate of change. The average rate of change in a relation is the change in the quantity given by the dependent variable, delta y, divided by the corresponding change in the quantity represented by the independent variable, delta x, or change in x. For a function y equals f at x, the average rate of change in the interval a less than equal to x less than equal to b is. So before I even go to that part, as soon as you see delta y and delta x, you're saying you're taking delta y and you're dividing it by delta x. Does that like ring a bell of something that you studied in math? So we've never seen this before in your lives. Slope. Okay, so slope. Okay. Hallelujah. So a rate of change is really a slope. And if your function is linear, really easy. Slope is your rate of change. Okay? But what if your function isn't linear? You can still find the average rate of change by basically saying, so I'll give you an example. So I'm going to draw a function. Okay, and you can do a whoop too. Okay, just draw a random function. We're going to call this y equals f at x. Okay. If I pick a point here, and that's A, what would the y value be of that function? In general. So it's just a generic function. If that's A, then how high is this point? It is how high? How would you find the y value? So what would be its y value? So remember, you input A into the function. Oh, f at A. Everyone makes this making sense? Okay. If I find another point here, and I call this point B. Okay.
Excuse me, Attorney, would all teachers sit down period 4 and all those standing attendance, please? Thank you.
So this one should be easier then. So if this is at B, the y value here is f at B. Okay. So if I want to find the average rate of change, I want to find the change in y over the change in x. So the average rate of change of f at x on the interval a, b. Very wordy, but you guys get that's what we're finding. The average, ROC, short form for rate of change. Everyone good with that? I'm going to be using rock all the time here. We're going to rock it out, okay? So average rate of change of f at x on the interval, closed interval AB is, how would you find the change in y here? You would do what calculation? I want to know how far this is between the y's. I would do y2 minus y1. What's your y2? F at b minus f at a. F at b minus f at a. All over the change in x. B minus a. There it is. What is this going to tell you? It's going to tell you the slope of this line. Okay? And it's going to, so it's basically going to tell you how fast it changed from that point in time to that point in time. Is that a good approximation of what's happening for the graph over that interval? not horrible, but at least you know I started at A, I ended at B. My Y value started at F at A, ended up at F at B. So it's a way of saying how fast it changed. Is everyone good with that? So we call it the average rate of change. So the big new thing here is you don't have to start with a linear function to have a rate of change. You can start with any function, and as long as you're told when the beginning and the end of the interval are, you can figure out the rate of change on that interval. You literally just are plugging into slope formula. Okay? So the following, we're going to do some examples just to kind of show how this works. So the following table represents the growth of the bacteria population over a 10-hour period. During which 2-hour interval did the bacteria population grow the fastest? So the thing with this one is, guys, is there a function here that you're plugging into? Or is this just, like, when you're looking at this, would you agree this is, first of all, let's ask this question. Is this a function? Because as time is increasing, what's happening to your number of bacteria? Increasing, right? So you have your big bacteria increasing over time. So now, what you have to think of here is, if I want to find during which interval did the bacteria population grow the fastest, I want to find the average rate of change on every 2-hour interval, and see during which time period did the population grow the fastest. Okay. Well, you're gonna basically use this formula. The only problem is, instead of you substituting your x values into a function, they've already given you the y values. There's no f at x that you plug 0 in to get 850. They're already just telling you there's 850. Because maybe they don't have a function for this. This is the data they've collected, and you have to just use that as your information to figure out rate of change. Okay. So sometimes rate of change might be based on a function, sometimes it might be based on numerical data. So let's do it. So the proper form to set this up, so there's lots, I left a whole, basically half a page of blank for this, because you're going to have to do how many calculations here? 5 calculations. Because you're doing during every 2-hour interval, you need to do a calculation. So it'll be average rate of change of, for this one, you can kind of avoid the of part because there's no f at x. But you can say average rate of change on, I'll make life easier for you guys, on the interval 0 to 2 equals. So what's the calculation you're doing for the first one? Going to be your y values, difference of y over difference of x, delta y over delta x. So the numerator is going to be 1,122 minus 850 all over 2 minus 0. So 1,122 minus 850, let's grab those calculators. We're going to use them that much so far. Blow the dust off the cover. Okay. So 1,122 minus 850, and then divide the result by 236. 136. What would be the units here? What per what? It's whatever is in the, whatever you calculate in the numerator per whatever you calculate in the denominator. Bacteria per hour. Does everyone understand why it's a rate of change? Okay, you've just calculated how fast the bacteria population changed from 0 to 2 hours. I'm going to press pause on the video, and let's find the other 4 calculations. Good. Okay, so these are the remaining 4 calculations of the average rate of change on each of these 2-hour intervals. And our conclusion is, during which 2-hour interval did the bacteria population grow the fastest? So therefore, the bacteria population grew the fastest during the, which interval? 8 to 10 hour interval. Again, it's just a matter of picking the largest number there. Okay? And so what's your suspicion of how the bacteria are growing? What trend do you think it's following? Most likely exponential. That's the typical bacteria question. You probably saw your exponential unit in functions, right? Doubling period, remember all that fun stuff. So there's no guarantee, because it might not be, but I think we can expect, since it increased every time. If you drew an exponential function and you drew those rates of change, you don't have to draw this, but just a visual. If you drew it and you drew through every 2 hour interval, I'm not going to be able to do it. I'm just going to do it like this. Do you guys get that if I draw little line segments for every 2 hour interval here, do you see what's happening to my rate? The slope's getting steeper and steeper, so therefore it makes sense that the rate of change would be increasing and getting increasing. Okay? Makes sense? All right. So that's that question. So far so good? Okay? And then last example. So a company that sells sweatshirts finds the profit can be modeled by P at S equals negative 0.30 S squared plus 3.5 S plus 11.15, where P at S is the profit in thousands of dollars and S is the number of sweatshirts sold expressed in thousands. Calculate the average rate of change in profit for the following intervals. So do you see, this time it's me a teeny bit more work, because instead of just giving a table with all the info, what have they given you instead? Well, they're giving you the intervals, but then they've given you the equation. So they have an equation that models profit here. So instead of just reading off a table and just plugging into your formula, you have to actually substitute values into the function to get the numbers. So you're going to have to do a little bit more number crunching on your calculator. A little hard, a little bit more work. But it's the exact same procedure. So I'll do I, we'll do together, then I'll press pause in the video and we'll do the other three. So the format here, so average rate of change of, gotta use the right formula, of P at S on the interval, and this is the interval 1 to 2, equals. So your function notation would be P at 2 minus P at 1 all over 2 minus 1. Is everyone okay? That's me using that F at B minus F at A all over B minus A, just changing the A and B to 0 to A and B to 1 and 2, and changing the function name to P, because that's what it is in this question. Okay? So what, instead of you going, okay, what is the Y value when the number of sweatshirts is 1, technically 1 means 1,000, right? That's what they told us in the question. That profits in thousands of dollars, S is numbers of sweatshirts in thousands. So this would be, as the number of sweatshirts sold increases from 1,000 to 2,000, how fast is my profit change? Does that make sense? That's really what you're finding. So now, how are you going to get those numbers? You have to plug 2 into the formula and get a number. Plug 1 into the formula and get a number, and then subtract, and there you go. The denominators are going to be really nice here, aren't they? The denominators are going to be really nice here, aren't they? Because they're all, how far apart are your intervals here? 1. So you got 1s all the way along. Okay? So when you get your answer, you could probably, what you want to do is just kind of do a number minus number step, and then just your answer will be a dollar amount, right? Now here's kind of a neat thing. If your number of sweatshirts are in thousands, and the profits in thousands, when you get your answer, or both are in thousands, when you get your answer, it's actually per sweatshirt. Does that make sense? Because if it's like you get the profit on 1,000 sweatshirts divided by 1,000 sweatshirts, you would get 1 per sweatshirt. Does that make sense? Because both of these are in thousands, when you get your answer, it's going to look like a dollar amount, and that's per sweatshirt. We good? Okay, let's do that. Let's do it. So can someone quickly put 2 in there? So on your calculator, and some of you might have kind of neat calculators where if you do this once, then you can use the backspace button and just replace the input. Does everyone know what I'm talking about? Yeah, that's not good. Okay, so negative 0.30 times 2 squared plus 3.5 times 2 plus 11.15. What do we get? No. See, as of now, I'm assuming everyone can handle the substitution step, so I don't need to see like the 2 squared, the 2's being subbed in with brackets. You just do it on your calculator. So what is it? 16.95. Okay. So, what does that mean? On its own, just that 16.95 means that when you sell 1,000 t-shirts, your profit is 16,950. Does that make sense? But then if for 1,000 sweatshirts, it's 16,950. For one sweatshirt, it would be $16.95. Yes? Make sense? Because it's like you're just removing 3 zeros from everything. Okay. So do it for 1. So you put 1 in there and you get what dollar amount? $14.35. So if you sold 1,000 sweatshirts, you would have a profit of $14,350. So one sweatshirt would pay a profit of $14.35. I do my subtraction here. $16.95 minus $14.35. You get $2.60. $2.60 per sweatshirt. I'm kind of going, let me write a lot tinier. Sweatshirt. Okay, so then basically you're going to repeat this process to get the other values of the rates of change, okay? So it means that as your number of sweatshirts, if the number of sweatshirts have increased from 1,000 sold to 2,000 sold, you're making an increase of $2.60 per sweatshirt, or $2,600 per 1,000 sweatshirts. But that's awkward to say, so that's why I'm just changing it to per sweatshirt. We good? Pressing pause. Let's do the other 3 calculations. Okay, so we found all of the intervals here, and we've calculated the rate of change on each interval, and we end up with these 4 rates of change. So we've calculated the average rate of change of profit for the following intervals. So a question that was just asked was, does this mean it's a bad business because my rates of change are decreasing? Well, not really. It all depends on what the function is that models your business. Do you guys remember what's been the function you've been using all along to model profit, revenue, and profit? Remember, you've been seeing these questions for your 3rd year with revenue and profit questions. What's the function that's been modeling these? Quadratic, right? Quadratic models profit. So when you have if you drew a quadratic, just like we just did with the exponential, if I draw a quadratic and I start dividing it into intervals, what happens as you get closer and closer to the vertex? If I start doing rates, do you see what's happening? I have a really steep rate at the beginning because there's such a big difference between where the y values are. So it's going to have big numerator over teeny denominator, right? Well, the same denominator, but then as you get closer and closer to the vertex, it's getting closer and closer to being a 0 rate of change. Because that's actually whenever you were asked these questions before now, it's always been what price or how many shirts should they sell to make a maximum profit? You would pick the X value of the vertex because you want to still make a max profit. But as you get closer and closer to that, if you want to think about rates of change, your rates of change are actually getting smaller and smaller. But as long as the rate is positive, you're still making more money. If I kept going, if I went 5 to 6, 6 to 7, 7 to 8, what's eventually going to start happening? You've been noticing what's happening with these numbers. Eventually the rate of change is going to be negative. And that's your clue of, I think I've passed the max revenue. Now I probably don't want to make any more sweatshirts. Now I'm losing money. Does that make sense? Because that's the whole point. Like you use this to model your maximum profit. you'd be not a great business if you start, I'm still going to make my sweatshirts. You're losing money now. Okay, so you want to just probably stop making sweatshirts at that point. Okay, so we kind of answered these kind of just informally. Let's do it formally. As the number of sweatshirts sold increases, what do you notice about the average rate of change in profit on each sweatshirt? What does this mean? So the average rate of change in profit is decreasing, meaning, well, what does it mean then? So what did I kind of say? So if it's decreasing, it's meaning my profit, sorry, yes?
It's reaching the vertex of the function or your maximum profit.
Yeah, meaning the the intervals are getting closer to the location of maximum profit. Does that make sense? The location of the maximum profit. Well, break even is revenue minus cost, so that would be more zeros, but when profit is zero, that's usually a break even point. So we want the profit to be actually the max we can earn. Okay. So you can, and then you want to say vertex of quadratic, if you will. And again, picture's worth 1,000 words. You can always just do that too, right? You can draw a little picture and just say, hey, look what's happening. My slopes are decreasing. And if you go beyond the vertex, they're still decreasing. They're getting more and more negative. That's still the definition of decreasing. More and more negatives, decreasing. So even if you kept going, they'd still go down. So again, I've given this away now too, but hopefully we all kind of knew this was happening. So predict if the rate of change in profit will stay positive. The answer is no. No. It will become negative once the intervals pass the location of the vertex. Everyone okay with that? Again, visual. Okay, here's the vertex. Positive, negative. Okay? Happiness? Okay. So, there's some assigned questions at the bottom of that page. It's your call. I'm going to tell you right now, there's not going to be like a page of these on your test. I think it's a waste of time for you. Okay? But will there be, for this function, find the average rate of change on the interval -2 to 5? Yes, that's fair game. Okay? So I've assigned those questions. Those are the practice for average rate of change. You decide if you want to do, for some of them it might make sense just to do the alternate ones, like you know how much you want to practice. As long as you know, if I ask for an average rate of change, you know what you're going to do. That's all that you really need to get from the homework here. Okay? Now, starting on, so as it stands right now for you guys, we're done the 2 lessons. I'm going to close off the video. Thanks for listening. Have a great weekend.